we were just talking, maybe consolidate some things in the earlier talks. Okay, so we start with things that I talked about at the end of the talk on recognizing the homology of a submanifold. So let me just give a little more depth and clarity on what I was saying. Recall the situation as follows. Here we have some kind of submanifold L. Not compact, contained in some interior space. And we have then some kind of probability measure of that, uniform probability measure, and we're drawing points x bar from that. In the meantime, we define the condition number, which reflects on how large we can make a tubular neighborhood around this before it comes into contact with itself. So here we would have tau giving the distance to the edge of the tubular neighborhood from the manifold straight out along perpendicular to the tangent space. This is tau from assure that we keep the tube intersecting itself. That's an ingredient. And then we have various things connected to tau. In particular, we have points x belong to x bar. We've taken an epsilon neighborhood about these to give us a neighborhood u. U will be contained then in our 2 given by the number tau. Okay? And now, by definition of tau, there's a projection of tau onto the manifold. Because every point in here has a unique closest point to M by this construction. Okay, so we have this map that will take, for example, everything along this section here. This, of course, is a normal high-dimensional space, but this picture will take everything here to this point here. So for pi, we'll take this line to this point. Over here, there's another out of the same space here, which will get mapped into this point 3 pi. So this, we have already at hand. And what we want to do is to show homology of mu, so we can restrict pi here. Part this one here, this is pi. Again. So we want to relate the homology of mu to the homology of M. So this map. Number of components of u, for example, should be the same as the number of components of M. The idea is now u, we can compute everything for u. We can compute homology of u. So u is algorithmic. And we have our confidence and so on. So we want to go from things we can compute to things we'd like to know, what number of components. Okay. So the idea is we look at pi from u to M. And I want to show, if we take a point P belonging to this, the pi inverse of P is intractable. Well, I'll do this in a very specific way, so if you don't know intractable, then it doesn't become important because we'll see a very specific contraction. How it's trivial in a sense. Pi inverse of P is pretty trivial like in this picture. It's just like not quite a ball, but it's close to a point. Okay. So pi inverse of P I want to represent. Okay, so how is that represented? Remember now u, by construction, is the union of all balls of epsilon radius of x over all x belongs to x bar. That's my definition of U. That's the empirical x bar is given to us. Epsilon, we have. Okay. So pi inverse of p then is the following. It's going to be, everything is in U. We're looking at this as an object in U. So it's going to be the union b epsilon of x. X belongs to x bar. But now we have to see these things just in this part here. Okay, so what we do is we intersect those balls with the normal space, with this tangent space, with this, I'll write this tangent space here, p sub p. So I have to look at the normal space of all vectors which are perpendicular to that. That's going to be pi inverse of p. See, p is defined by taking that normal space to p, higher than the u. So, in other words, what we'll do here is we intersect each of these balls with p, p, perp. But the trouble with that is, p perp contains these things over here. So it cannot, this is not part of pi inverse of the point p. It's just these. The pi and the physical neighborhood about here. So what we have to do is to intersect again with, say, a tau neighborhood or epsilon tau neighborhood is a tau ball about, and that keeps us here. Okay, so this is what we're dealing with. Pi inverse of p is described just like I've written here. So what I'd like to show, this is tractable to a point. So now you can see we're getting into something pretty geometrical. I want to just illustrate how geometrical and what the solidity and how the proof goes. This contains the following set, trivially, the same union over a smaller set. X belongs to x bar, and I restrict x to belong to epsilon ball among p. So I'm taking this union over a small set, namely I'm taking this over all the things nearby here. So the x's here are close to p. Okay, so this is surely a bigger set than this. Okay. So let's call this set here star. And what I want to do is two things. I'll do one thing and this other I'll just sketch. The first thing is to show this one here is contractible to a point. It's a star-shaped neighborhood. Then the second part of the lemma is to show these are equal. That's the result of the part. So these are actually equal. This is contained in here, but they're actually equal. So we have lemma in two parts, but the most normal part is equal here. So I'm laying down the structure of the main part of the theorem. This is the main crucial part of the whole theorem. And so now let's check that this is contractible. So let me work over here. Okay, so the idea is this. I want to show that this union over here is contractible. So I take any v belonging to star. Any v. So that v, that point v, belongs to the epsilon of x. So v belongs to see if you have this right. That's pretty obvious, isn't it? Some of you, if v belongs to here, first of all, it must belong to one of these. Belongs to v epsilon of x. that type. They're intersected by linear things. Well, certainly any V in here will belong. Any V in here will belong to one of these, right? And moreover, that X is close to a P, so that X belongs to here. No. Wait a second. Yeah, that's right. So X belongs to here, and P belongs to here, right? Because of our hypothesis, down here, X belongs to B epsilon of P. So P belongs to B epsilon of X. Right? So P belongs to this set, B belongs to this set for some X, P for some X. Okay? So any of V belongs to one of these, and P belongs to all of these. So in other words, B, P segment belongs is contained in B epsilon of X. The second case. That means this is convex and it's only intersected with these other convex things. So we can track in the set. Okay. I think that's a pretty rigorous group, maybe something more than obvious to any of you instances. So it's, as I say, it has this kind of shape. It's compatible but not convex. Any questions about that argument? Okay, so let me just say a few words then about why these are the same. So these are the same. Okay. Any questions? Okay, so I want to show you more. I'm not going to give the indication here. Okay, so I want to take something in the top set and show it belongs to the bottom set. Alright? That will give you top. Everything in the top belongs to one of the bottom. Okay, so now I use that weapon that I stated before. We have epsilon, x bar is epsilon over 2 dents. So here's the picture we get. Here is maybe manifold. The tangent of the manifold is like this. And pictorially, this would be the orthogonal to the tangent space. Here might be a point Q, which is within epsilon over 2. Here's the picture of the epsilon ball about P. So here is Q, like epsilon dense. So Q belongs to x bar, and this distance is epsilon dense. So this is one of the balls that is in this place here, the bottom. Okay, so we take a ball like that above Q. Take an epsilon ball above Q. Here's B epsilon. Now what I have to do is to take something in this larger, possibly larger set, and show this in here where we intersect this. So now I'm taking some U along the x bar, which is not in the set, not in this ball. It's farther away. It's not in the bottom set. Correct. It's restricting only sample point from the epsilon of T. So now I get the sample point U outside of epsilon T. So now I have to show that the epsilon ball about U is actually contained in this already. That's the geometrical argument that has to be done. And now let's make it plausible. And here we have to use that Q and U are in the manifold. So in the special case, if the manifold were very flat, say Q were at this point, and U were over here, then the ball about U would just touch this point, and Q would contain quite a big feature. So you can see already, if the manifold is very flat, this is going to be immediate. The manifold just passes through here flatly, then U has to be down here. And so this ball about U is just going to touch at one point. So surely it will be contained in the ball about Q, because Q is pushed away into epsilon over 2 here. Okay. So what we have to argue is now allowing some curvature. We have to allow a different situation. So the curvature is the property that in the worst case, the manifold would come down like this and up here like this. But not curve too much because of the tau condition. Epsilon, remember, this is square root of 5 over 3 times tau. And that prevents the manifold from curving too much. And so if you put all that together, then one has the little delicate argument working with Pythagorean triangles to finish the proof using the numbers square root of 5 over 3, or mainly that number. That is some sketch of the main lemma behind the theorem of homology. So I think most of you could reconstruct this with just sitting down in time and understanding what is there. You make all these worst case analysis with Pythagorean triangles and restrict certain planes in Euclidean space. So any questions on that, or any questions about any aspect of that talk on homology and some manifolds and the constructions, the algorithms for finding a number of components? Okay. So what I'll do next then maybe is to give some part of the picture that's important for this work on Shannon theorem. Because there was one important aspect that I didn't get into for reasons of we want to spend too much time on too many things. But there's an underlying aspect that I'm sure many of you guessed, and I want to make that a little clearer. And it also gives some extension to how to do for the case with poor data. So we're back to Shannon. Okay, recall we have these spaces H, K, and P bar. These were generated by these kernel H and C functions with a reproducing kernel type of inner product. So this is a working space. So you think of working in this space. This in the compact domain space X, this would be a P-bar finite set. In the Shannon case, when you're working all of the space, this is the infinite set. Set like the integers in the Shannon case. So this is our working space, so to speak. And now we're given samples. Y, all right, y sub x. Well, first of all, we're given a data x bar, which could come from a well-determined input, x bar, as in scientific computation, or may have come from some kind of a random draw with respect to some probability distribution, like a learning theory. For the moment, I'm just using x bar for what it is. It's a discrete set in x, of which we are sampling from. We have a probability distribution on x cross y, on the measure on x cross y with these distributions px, which for x1 to x bar. These model the noise in the sampling. The noise at the values, not there's no probability in x space. X has no probability. Along these fibers in the y space for each x belongs to x bar. These have certain conditions of it. Okay, so yx then going to be in the form of some unknown function, say hkt bar. So this will be the form f of x, f unknown. Think of this something like a regression function for some major, which we don't specify, probabilities put into this eta x. So eta x is drawn from rows of x, conditional measure of x. And we have a stipulation if we're in the infinite sample case, then the support of these measured row x has to decay in a fashion that puts them in rule L2. Okay? This is recollections. And then, so the sampling is related by a linear operator. He gave us some b in rule L2 or t bar, and then our reconstructed function f total is equal to sum dp a2. P belonging to t bar. Right? Now, there's underlying all of this. This is in the rich-gated case, we have the estimates. I mentioned last time, f total minus f, k norm less than epsilon is estimated with high confidence. Confidence given explicitly by a formula I did last time. Would, assuming we had rich data. Okay, so now we want to do a couple of things. We want to put this into a situation of optimization. I think many of you would have guessed this already, but there's underlying this is a optimization problem. And it's important to understand, for example, the algorithm that I mentioned last time. It's a solution of a quadratic optimization problem. So what is the optimization problem? Well, let me cover everything at once. Case of poor data and the situation I discussed here. So now we want to allow poor data as well. And even here, there's something that might be important, and that is, this is everything I've said is tight. I mean, everything else, everything is okay, but the linear algorithms could be conditioned perhaps better. Sometimes it could be poorly conditioned. They're not ill conditioned, but it could be poorly conditioned. One might want to give some conditioning. And the way one does that and deals with the poor data case at the same time is to do regularization. So we want to use a regularized optimization problem. And that problem is the obvious one. Minimize over all f belonging to our universe hk t bar the following: sum f of x minus y sub x squared. Y sub x sample given this way. You can figure that as this empirically given sample over all x belonging to our maiden set x bar. This is given, not t bar. So here we have t bar representation set. Here we have x bar in the sample set. And then we have to add on plus gamma norm f squared. So minimize that. Okay, so then the competitions. You can do this in a lot of ways. That we use functional calculus to find best suited for these kinds of things. The proposition gamma equals 0. Now this gamma here is some parameter now. Gamma equals 0. You get the old situation. You get get the, we can do that if the data is rich. We could take gamma here and get a unique solution to this problem. So that's part of the proposition. Gamma equals 0, we get there's a unique solution to this problem. Gamma equals 0, there exists a unique solution. And it's given by this expression for L. Given by L. P bar, X bar, and X bar, P bar. Inverse of this matrix is defining an object. Invert that on the condition of rich data. K, T, X bar, P bar, X bar. These are all matrices. Possibly infinite dimensional, but they're all matrices. These are all linear, all working with these little L2 spaces. And this, together with this equation here, that and this, these three together is the solution of this realization problem. When gamma equals 0. Okay, so this complements very much what I said last time, because last time I just produced this algorithm without saying anything motivated. It doesn't matter in some sense because we have the algorithm, one knows what to do. And moreover, we get the estimate. So we do all of this without mentioning the optimization, but the optimization is at least philosophically important behind all this, conceptually. So it doesn't need for the logical or practical development. One doesn't need this because the algorithm is given explicitly here, and the sample error is no optimization. But it certainly is important to see that underlying that is this. Okay? Right now, we can take gamma bigger than 0. Now, if we get gamma bigger than 0, we still get a unique solution to this problem, gamma bigger than 0, because of this penalty term, this term here. There exists a unique solution. Here we had rich data. And gamma bigger than 0 deals even rich data with poor data. It deals also with the rich data case, sure. But what's important is that it deals with the poor data as well. And what one gets for L, one gets the following. The solution then of this optimization problem, the case general gamma, is the following. We write L, same formulas in here and here, exactly the same. We just have to change the expression for L, the linear operator. L is equal to K, same as before so far. That may not be invertible now. Right? But we add on this non-negative matrix. This is a semi-definite matrix. So it's not too bad. We just add on a little more. Gamma, K, P bar, P bar. And this is a matrix we assume is bounded and had a bounded inverse. So we put this in here, inverse. So this is invertible now. The K is positive, always. So this gives the algorithm for the poor data case. Just write in here K, X. Now, do I got these X bars, P bars, bars? I think this is right. Yeah, X bar. These should be P bar, X bar. Right. Because this goes from little L2. Yeah, so this is a map In all cases, L is a map from little L2 of X bar. That's where the data lies. And it lands this in the representation space, little L2 of T bar. So B is in here. These are the way we want to represent things lying here. So L, and even the general case, those are the place where the data, or the output data lies, to the place where we want to represent things. And so this optimization problem plays a bigger conceptual role now, because this leads us to this picture of how to deal with poor data, rich data, and the same formula. Gamma equals 0. That will give us the previous circuit. Now we can take gamma positive, even with the rich data case, if we want to gain a little more regularity to that linear system. If we want to make that linear system better posed, we can still make gamma positive and get some push more positive in this term here. So this gives more conditioning to our linear. And if this is poorly, if it's poor data, then we need this to get a solution. So then we have the next theorem. Okay, there's Y and the next theorem, which extends the sample estimate to an estimate in the case of poor data. And then, of course, if the data is really poor, it's not rich, the estimate is going to be less satisfactory. Obviously, you're not going to get such a good estimate, and our estimate does have a term which looks like an integral and integration, and it looks okay. And so we get some estimates which give us back the old theorem in the case of rich data, and they give us some estimate in general. So we're estimating by now a term like D will depend on gamma, another thing. When gamma becomes 0, then we get the old term. If it's gamma positive, then we get some other terms which are there. They have to be there. That's the sample. That's the error analysis in general for the rich and for the poor data. And, okay, so maybe I will. Thank you.